Okay, so at this point, you guys, you should know the basic equation for work. You know, this chapter is called Work and Energy. So yesterday we said the basic equation for work is force times displacement. And the thing to know about this equation, I mean, it looks very simple. Just multiply two things together. But what do you have to know about this equation? The force doing the work has to be parallel to the displacement. Okay? Now, all of this stuff, work and energy, it's all measured in what unit? The joule. And you have to know what a joule is. A joule is a kilogram meter squared over second squared. So joule is equal to kilogram meter squared over second squared, which, yes, you have to memorize it, but it's not that hard, because all you got to do to figure out what a joule is pick any equation that's in joules. So look, kinetic energy, what's kinetic energy going to be in? Joules. What's potential energy going to be in? Joules. So you could pick any one of these. Like, let's just pick potential of gravity. What's mass measured in? Kilograms. What's gravity measured in? Meters per second squared. And then what's height? Meters. So what does that all simplify to? A joule. So you can figure it out really easy. Okay? All right. So you should know the three forms of mechanical energy. Mechanical energy, I just call it useful energy. Not all energy is useful. You know, like you guys drove here in a car, you parked your car in the parking lot, and then what is, as you walk away from the car, what's leaving your car? Heat. Is heat a form of energy? Yeah. Is it useful? No. Well, not in that context. I mean, heat can be useful, but you know, as heat escapes your car, that's energy, but it's not mechanical energy. So in this class, we have three forms of mechanical energy. Kinetic energy is the first one. And what is kinetic energy? The energy of motion. If an object's moving, it has kinetic energy. Then we have potential energy of gravity. Now, what do we mean by potential energy? Potential energy is like a fancy name for stored energy. So can gravity store energy? Totally, dude. Totally. Did we talk about this? The way I have kids, because kids have trouble understanding how gravity can store energy. So let me put it to you this way. So see this girl right here? Pretend this is like a steel ball. I'm just going to make it dramatic. This is like a big, heavy, like bowling ball. Let's say it's a bowling ball. And you are laying down here at the bottom of the cliff. You're enjoying the afternoon. The sun is up here. Oh, it's a beautiful day. And you're laying down here, soaking up the sun. You got your eyes closed. And then this girl drops this bowling ball on your face. Would you feel some energy there? Yeah, man. A bowling ball crashing down on your face, you would be feeling the energy that was one time stored up there. You know, gravity can store energy. You know. So anyway, but the one thing we got to talk about here is the equation, potential energy of gravity. So M is easy. What's M? The mass of the object. What's G? Gravity. Don't make gravity negative here. If you make gravity negative, you're going to have negative potential energy, which is possible, but you know that means something different. So you're going to plug in the absolute value for gravity. H is the one tricky thing. H is defined as the vertical height above the 0 point. It's in the Spaldo notes. It's the vertical height above the 0 point. Now guys, what's the 0 point? The 0 point is where you measure H from. Where does it go? Well, the honest answer to that, you can put the 0 point wherever you want and the problem's solvable. You know, you could, for this situation here, you could be like, I'm going to put the 0 point there, you know. So then the ball would start with positive potential energy, and then as it passed the 0 point, it would go into negative potential energy. It's doable, but why make life hard? My advice to you is to put the 0 point at the lowest point in the problem. So if this girl drops the bowling ball Where do you want the 0 point to be? Down there. You want the 0 point to be down there. Let me ask you a question. Does this bowling ball does this ball up here have potential energy? So somebody say yes. Yes. Somebody say no. No. You're both right. It's yes and no. Because what does it depend on? Whether or not the ball has potential energy depends upon what? Where's the 0 point? Are you putting the 0 point up here? If the 0 point's up there, then how much potential energy does the ball have? 0. If the 0 point's down here, then it's got potential energy, So this will all make more sense as we do problems. My advice to you, here's my advice. Put your 0 point at the lowest point in the problem. So whatever problem you're working on, identify the lowest point and be like, boom, that's my 0 point. Okay? That's how you're going to make life easy. Okay. Can energy be stored in a spring? Yes. So let's look at this. Okay, so here we have a toy gun. The way most toy guns work, it's spring operated. So you take a spring, and what happens to the spring? The spring gets compressed. Smush, 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 smush. When this spring is all compressed, is there energy stored in that gun, in the spring? Yep. So how do you find the energy stored in a compressed or stretched? If you stretch a spring, there's energy in there also. So how do you find energy in a stretched or compressed spring? The equation is 1/2 kx squared. Yesterday we talked about K. What is K? The spring constant. And it's different for every spring. Every spring has its own. The unit, who wants to be the awesome student for the day? What's the unit for the spring constant? Boom! A plus. Newton per meter. And I want you to understand this. So for example, this spring, this toy gun, let's just say the spring constant of that gun, of the spring, is 50 newtons per meter. What is 50 newtons per meter telling you? It's telling you if you take that spring and smush it 1 meter, what force will the spring give you? 50 newtons. What if you take the spring and smush it 2 meters? 100 newtons. It's 50 newtons per meter. And by the way, that's whose law? Hooke's law. Force of spring equals negative kx, where x is displacement. Hey, what's that negative all about? Negative kx? Well, the negative is simply saying the force of the spring will always be opposite the displacement. So if you pull a spring down, the force of the spring is up. If you push a spring up, the force of the spring is down. That's what the negative's there. But the truth of it is, when we start doing homework problems, you're just going to be going, okay, force of spring equals kx, and then you'll figure out the plus or minus. Like which way is the spring pushing? Is the spring pushing plus, or is the spring pushing minus? So don't get all caught up in the negative. Kids get really confused by that negative kx. All right, so now for the good stuff. You ready? This is good. So we're going to be talking about conservation of mechanical energy. Now, outside this room, you hear the word conservation, right? What does conservation mean? Like people talk about, let's conserve energy, let's conserve water, let's conserve our natural resources. What does that mean outside of this room? To use less water, use less energy. Is that what we mean in the physics sense? No. In the physics sense, what we mean is what we start with at the beginning of the problem is going to be equal to what we end with at the end of the problem. Initial equals final. So we're applying this to conservation of mechanical energy. We're applying this conservation idea to mechanical energy. So just so we're really clear, what we're saying here is the mechanical energy at the beginning of a problem is going to equal the mechanical energy at the end of the problem. Okay? Now, will this always be true? No. And let me tell you why. we're kind of starting out easy, and then by the end of the week, we'll be looking at situations that are harder. Look, what we're talking about today is only true if conservative forces are doing work on the object. And this is real easy because, look, in all of first semester, there are only two conservative forces. The two conservative forces are gravity and springs. So look, if it's not gravity and it's not a spring, then what is it? It's non-conservative, which we're not going to talk about today. We'll talk about that later. But I just kind of want you to understand what we mean by non-conservative. So look, if you're looking at a problem and you're like, okay, this object is moving and, oh, the only thing doing work is gravity, or the only thing doing work is a spring, then what we're saying today is true. Mechanical energy at the beginning equals mechanical energy at the end. Okay? So let's just talk about that with this in mind. But, just put it in your head. If it's not gravity and it's not a spring, then it's not conservative. And by the way, what is the number one non-conservative force? Can anybody guess the number one non-conservative force? Takes away energy, takes away mechanical energy. Friction. Dude, you're on fire today. Friction. Guys, if friction is present, the mechanical energy at the beginning and the mechanical energy at the end will not be equal. Okay? So we'll have to account for that. We'll do that later in the week. So this situation here is no friction. On this diagram here, we're going to say no friction. Okay? So look, we have this ball. The ball starts at the top of the hill. Now, we have 100 joules of potential energy and 0 joules of kinetic. Oh, and the 0 point for this situation is the very bottom. The 0 point is down here. This is the 0 point, all the way at the bottom. So how much mechanical energy does this ball start with at the top of the hill? So how do you figure out mechanical energy? Mechanical energy is kinetic plus potential. So how much mechanical energy do we start with up here? 100 joules. All right, now the ball can take two paths to the bottom, and we'll talk about both. The first possible path is the ball goes down the hill this way. The second possible path would be it goes over the backside like that. So let's do the first path. So the ball rolls down this hill. There's no friction. Okay? At this point right here, the ball has 50 joules of potential energy. That's a given. So my question for you, and it's a real easy one, don't overthink it. How much kinetic must it have? It's got to have 50, right? How did I know that? Because kinetic plus potential, the total mechanical energy needs to stay the same, right? Assuming, again, what is this assuming? No non-conservative forces, no friction. This ball does not have a rocket on it. Because, a non-conservative force could also add mechanical energy. Like if this ball here were like rocket powered, then the ball would be picking up mechanical energy, right? So assuming no non-conservative forces, the mechanical energy stays constant. Now, the ball rolls across this flat part. So what are these numbers going to be? What is the potential energy going to be? It's going to be 50. Now, how do I know that? Because look, what's the equation for potential energy of gravity? mgh. So from here to here, did the mass of the ball change? No. Did gravity change? No. Did the height change above the 0 point? No. So therefore, potential energy of gravity stayed the same. So how much kinetic do we have? 50, because these need to stay constant because we have no non-conservative forces. Hey, what's the only force doing work in this problem? Gravity. The only force doing work is gravity, and gravity is conservative. Gravity is conservative, which simply means mechanical energy initial will equal mechanical energy final. Okay? All right, so the ball keeps rolling at the bottom of the hill. Now we're at the 0 point. So how much potential energy? 0, because the h is 0. So what must the kinetic be? 100, because the two of them need to add up to 100. Mechanical energy stays constant. Now, let's go over here. So the ball goes over the backside, falls down like this. Right before the ball hits, how much potential? 0. So the kinetic must be 100. Okay, so does this basically make sense? All right, now I'm going to challenge you. So any questions here? All right, so here we have a kid on a skateboard. Oh, and again, we're going to say no friction, right? Because what would be happening if friction were present? Would friction be adding mechanical energy or removing it? It'd be removing it, okay? So we say no friction. Now, you have the mass of the kid, you got the velocity of the kid, so you have enough info to fill in all of this. So I'll give you guys like 5 or 10 minutes. We'll turn on some tunes. So based upon what we just said, oh, and you're going to need the equations. You're going to need this. What's the equation for potential of gravity? mgh. What's the equation for kinetic? 1/2 mv squared. You're going to need that. Everybody put your 0 point. I mean, just like I said, if you really, really, really wanted to be like, make life hard, you could stick your 0 point like boom, like right there. Spaldo, that's my 0 point, right? But then what's the bummer? And you would have to define this. You would have to say like, all right, my 0 point, you'd have to like specify what that is. But what would be the bummer with doing that? This potential energy that the kid starts with would be what? Negative, because he'd be below the 0 point. So you want to avoid that. Where should you always put the 0 point? At the lowest point. So for this situation, everybody put the 0 point down here at the lowest point. That's the 0 point. Okay, so fill in everything. So the kid starts here at the bottom. His mass is 60, including the skateboard. Somebody asked about that earlier. You can assume that it's kid plus skateboard. Velocity is 8. So we can find his kinetic energy. How do we get his kinetic energy? Plug into 1/2 mv squared. That's the equation for kinetic. So this comes out as 1,920, I believe. 1,920 joules. Okay, how much potential energy does he have? 0, because he's on the 0 point, right? 0 joules. mgh, if your h is 0, if you're on the 0 point, you have 0 potential energy. All right, so what's his total mechanical energy? How do you get mechanical? You add kinetic plus potential, so that's 1,920 joules. Okay, now his velocity is 8, h is 0. All right, so then he hits this hill. He starts to go up, up, up. So at this point, he's 1 meter up, so h is now 1. Velocity is a question mark still. Mechanical energy, we know. It's got to be 1920. 1,920 joules. The whole idea here is that if conservative forces are the only forces present doing work, then mechanical energy stays constant. Now look, in real life, just so you got this, in real life, would his mechanical energy have stayed constant? No, because as he skates up the hill, what's friction doing? Stealing mechanical energy. In real life, if you take something and like slide it up a hill, the mechanical energy is not going to stay the same, right? Because friction. Oh, and what does friction do to that mechanical energy? Everybody go like this. Everybody. Like this. Now, rub your hands. Like this. What does friction create? Heat. Is heat a form of energy?
Yes.
Yeah, but it's not mechanical. It's not mechanical energy. So friction turns mechanical energy into heat energy. But here we're saying no friction. All right. So how do we get the rest of this? Well, can we find his potential energy? Yeah, because we have his H. So you plug in to mgh, and that's going to be what? What does that come out to be? That's right, 588. So now we can figure out his kinetic, because we know kinetic plus potential has to add up to 1920. So this is 1,320. Wait, what is it? 1,000? 32? Is that it? Okay, because they need to add up to 1920. Okay, so how do we get the guy's velocity at this point? Well, you take the kinetic energy equation. Velocity is going to be square root of 2 times kinetic energy over the mass. Right? Just rearrange the kinetic energy equation, and we find out that he's going, is it 6.7? 6.7 meters per second. All right, then he keeps going up, up, up. Now at the highest point, for a split second, his velocity goes to 0, which means his kinetic is 0. If you have no velocity, you have no kinetic. Okay? The total mechanical energy, assuming no friction, is 1,920. The mechanical energy stays constant, so all of his mechanical energy is now in the form of potential. Right? So the idea here is energy just moves from one form to another, but the total stays constant. Okay? So velocity is 0, and now we can figure out his h. So you take the potential energy equation, solve this for h. It's going to be potential energy over mg. Okay? So when you plug in, that comes out to be 3.2? I forget. So we'll say 3.3 meters. We'll round that to the 10th place. Okay, any questions on this? All right, so the last thing for today, I want to talk, this is going to be a great way to end our lecture. Okay, work done by gravity. Final slide for the day. Okay, you are going to be asked in the homework set, on the quiz, on the AP test, you're going to be finding the work done by gravity. So I want to show you something really awesome. You know, a great way to think of it. Because if you understand this, it'll be easy. What's the basic work equation? The very first one we ever learned. Force times displacement. What must be true about force and displacement when you're using this equation? They got to be parallel. Okay, so look at this girl who jumps off this diving platform. Well, actually, on the left side, she dives. On the right side, she goes down a slide. The point being made here is that the work done by gravity is the same for this and for that. It doesn't matter how she goes down, right? Whether she jumps off the left side and just like dives in the water, or if she slides down the slide, the work done by gravity is the same. So how do you figure out work done by gravity? Well, look, if you're solving for the work done by gravity, what force would this be right here? That's going to be what? The force of gravity. If you're looking for the work of gravity, then you're going to be using the force of gravity. Okay? Now, what is this displacement going to be? So keep in mind, the force and the displacement have to be parallel. So what is parallel to the force of gravity? So look, when she's here, force of gravity always points straight down, right? It's never at an angle. It's always straight down. So we got force of gravity straight down. So will the distance that we're using, will this delta x, is it going to be the length of the slide? No, because the length of the slide is not parallel to gravity. What distance, or displacement I should say, what displacement is parallel to the force of gravity? The height. Look at the height is parallel to the force of gravity. So ready? You're going to be like, oh, in about 60 seconds, guys. In about 60 seconds, you're going to be like, whoa, physics really connects together. Not yet, though, in about 60 seconds. Okay, so what is this delta x going to be? H, because it's parallel to the force of gravity. Dudes, what's the equation for force of gravity? It's mg. So watch, bring that down. Force of gravity is mg. Watch, ready for it? Bring the h. What is MGH? It's potential energy. So here's what I want you to put in your brain. Just be like, oh, work of gravity, that's equal to the potential energy of gravity. Okay? But I'm not done yet. Because look, I want to mention this. If you open up the textbook, which I don't know why you would, because you have the Spaldo notes, right? The Spaldo notes are like the cliff notes to the book. But here's what the book says. The textbook says work of gravity equals the negative change in the potential of gravity, which is highly confusing. You know, kids are like, what? The negative change? Which is true. But look, what's the negative change? The negative change. So what is change? Change is final minus initial. So the negative change would be initial minus final. Are you already confused? Look, don't do what the book says. Because the whole thing with this negative business is you need to be able to figure out, look, you got to be able to figure out, is the work done by gravity, is it plus or is it minus? And that's what that's what the textbook is trying to do right here. You know, look, to figure out whether the work of gravity is plus or minus, all you have to do is know the sign convention for work. The sign convention for work is real easy. If the work is being done in the direction of motion, that's plus. If the work is being done opposite the motion, that's minus. So, dude, do not do this. This is confusing. Confuse. Don't do that. What you do is you go like this. You're like, okay, here's what Spaldo said. Work of gravity is going to be equal to potential of gravity. Now, how do you figure out if it's plus or minus? Well, look, if the girl jumps off the diving platform and goes down, as she goes down, is gravity doing work in the direction of motion or against it? In, right? So as she falls, is that positive or negative? Positive, because gravity's doing work in the direction of motion. Now, what if she gets out of the water and starts climbing up the ladder? So here she is, and she starts climbing the ladder back up. If she's climbing the ladder, is gravity working with her or against her? Against her. So that'd be negative work. Easy. Make it easy. Okay, any questions? You like this, don't you?
Yes.
Okay, we're done.